Before we check your homework, I just want to review, kind of recap this lesson 15-2. So at the very beginning, on page 209, it just tells us to identify the different parts of a trapezoid. Remember, a trapezoid is a quadrilateral, which means just from hearing that, or just from being given that, that's a quadrilateral. We know it has 4 vertices, 4 sides, 4 interior angles, and we know that those 4 interior angles, their measures will sum up to be 360 degrees. So that's what you know when you see that. It is a quadrilateral. Then it tells us that a trapezoid is a special quadrilateral with exactly 1 pair of parallel sides. That means you must show that 1 pair of opposite sides are parallel and the others are not. You have to show that the others are not. So we have the 2 sides that are parallel are called the bases, and then the 2 non-parallel sides are the legs, and we identify the base angles and so on and so forth. Then we started talking about this special segment within trapezoids, and your textbook refers to it as the median. The median of a trapezoid is a segment whose endpoints are at the midpoints of each leg. Notice that it says the legs of the trapezoid. There is nothing special about a segment that connects the midpoints of the bases. It's only the segment that connects the midpoints of your legs. And there's 2 things you need to know about that special segment. This median is going to be parallel to your 2 bases, and it's also going to be the average of the lengths of your 2 bases. So very similar to the midsegment of a triangle. So we talked about that. We proved it using the mid-segment triangle theorem, and we talked about that for a little bit. The one thing we didn't get to spend a lot of time on was on page 210, dealing with the isosceles trapezoid. And so I do kind of want to pump the brakes right here and really talk about this and make sure that everyone's on the same page when it comes to isosceles trapezoids and why it works out that way. So here on item 7, it gives us some information, and it tells us that this triangle, the large triangle ABC, is isosceles with this segment AB having the same length as segment CB. Remember that if 2 segments have the same length, then by the definition of congruent segments, you can state that they are congruent. So I know that those 2 legs of that isosceles triangle are congruent. It also tells you that these 2 segments have the same length. And when 2 segments have the same length, then you can say that they are congruent by the definition of congruent segments. So this is the information that we have pulled from the given. And then it asks us, item 7 asks us a series of questions just regarding this one diagram. And I want to walk you through them and make sure that you can make sense of all of this. So it says that angle A is congruent to blank. So in the diagram, angle A here is going to be congruent to what angle? And you have to have some justification. And I want it to be a property, postulate, or theorem, not just because it looks that way. So angle A is congruent to which angle and why? Why angle C?
Because of isosceles triangle theorem.
Very good. So your base angles of any isosceles triangle are congruent. So yes, angle A is congruent to angle C. Why? It's because of the isosceles triangle theorem, the base angle theorem. From there it says, explain why triangle BDE is isosceles. And so they're talking about this guy right here. This is quite a large leap from saying that these angles are congruent to all of a sudden like, hey, you know why this is isosceles, right? And so there's a lot that we have to talk about before we do this. Let's look at the 2 triangles. We were told that triangle ABC is isosceles. They straight up told us that. And then they also told us that segment AB is congruent to segment CB. And then from there we deduced that angle A was congruent to angle C because of the isosceles triangle theorem. Anything that goes on the board should probably be in your textbook. And so we justified that by the isosceles triangle theorem. Well, there's another triangle within this diagram, and that is this guy right here. So it says explain why this triangle has got to be isosceles. Well, we were given that this segment was congruent to that segment. So that means this whole segment, AB, was congruent to this whole segment, BC. We were also told that a portion of each large segment was congruent to each other. So we can just use our logic and kind of just think through this and say, well, if the wholes are congruent, if AB is congruent to the whole BC, and then we're taking away a congruent portion, then yeah, whatever's left over has got to be the same length as well. However, if this was a proof, you would have to use segment addition and say that part plus part equals whole. So you'd have to say that the length of AD plus the length of DB is equal to the length of AB. That's just segment addition. Then you have to state the same thing for the other side and say that the length of CE plus the length of EB is equal to the whole thing. We call it CV. And then because we know that these two lengths are equal, we would set them equal to each other. That's just substitution. So that's just substitution, setting those two things equal to each other. And then we would have to use substitution again because we know AD is equal to CE. I'm going to plug that in for here. So this now is the length of CE plus DB is equal to CE plus EB. Again, that was just another substitution. And now I have the length of segment CE on both sides of the equation. So I can subtract that from both sides, and I'm left with the length of segment DB is equal to the length of segment ED. If the two segments have the same length, then I can state that they are congruent. Now that I've proven this one triangle has two sides that are congruent, then I know it's isosceles. So this is a very simple statement. It just says, hey, it's isosceles, right? But the explanation in the proof is quite in-depth. And so you need to write all of this just to state that that is an isosceles triangle. So with that in mind, now that we have proven that this is an isosceles triangle, then they jump up and they say, well, then explain why segment AC is parallel to blank. Well, if you look at the diagram, there's only one logical segment, and that would be segment DB. So explaining why these two segments are parallel, again, it's a very large leap, and so we need to really talk about this and digest this. This triangle that I have outlined in green E, we have come to the conclusion that it is isosceles, correct? So I know that this rule applies as well, that these base angles are congruent. That's justified by the isosceles triangle theorem. Well, these two triangles, the original one that we've been talking about, triangle ABC, the larger one, that's isosceles triangle. And then the one that's outlined in green ink that we just determined was isosceles, triangle DBE. What are those two triangles, other than both being isosceles, what do they have in common?
Line D, or line B.
D.
So we're looking at the green triangle that's outlined, and then this triangle. I'm looking for an object that they both have the full thing in common. I'm looking for a part of a triangle, so side, angle, something. They both share angle B. Okay, I was hearing vertex B, like that's just a point. So yeah, so angle B. They both share that part. So from there, if I want to prove this statement, part C, that these lines are parallel, and I'll do it in, let's say, red here. This is what I'm trying to prove right now. There's a lot I have to say. The three interior angles of this green triangle are going to add up to be 180 degrees. Correct? Is everyone okay with that? Okay. Then, same thing with the three interior angles of the original in this diagram. It's outlined in blue ink. Isosceles triangle. So measure of angle B plus the measure of angle A plus the measure of angle C, that's also going to equal to 180 degrees. So if I want to prove that these lines are parallel, I'm going to have to go through all of this. This is what I'm doing. I'm going to show that this angle here, angle BDE, has to be congruent to angle A. Once I prove that angle A and then this angle up here are congruent, then these lines are going to be parallel, because if corresponding angles are congruent, then I know lines are parallel. The only way we can prove lines are parallel at this point in this course is by those four special angles. We didn't show that alternate interior, alternate exterior, corresponding angles are congruent, then lines are parallel. We're going to show that same side interior angles are supplementary. The lines are parallel. We have a couple other ways. If we had the coordinates, then we could do what we did for the warm-up and prove that their slopes are the same, but we can't do that right now. And then if two lines are perpendicular to the same line, then those two lines must be parallel, but we don't have that. So we've got to work with these angles. That's the only way we can prove these triangles are, I'm sorry, that's the only way we can prove that these segments are parallel. So, what I would do in a proof is state this. This is the triangle sum theorem for both of those isosceles triangles. They both equal to 180 degrees, so I would set them equal to each other. They both have the measure, they both have the measure of angle B in common, so I would subtract that from both sides, and I would be left with this, the measure of angle BDE plus the measure of angle BED, and these are the two base angles in the green isosceles triangle. Those two, when summed up, is going to equal these two summed up. And you can just stop and just make sense of that. These three are going to add up to be 180 degrees, and these three have to be added to 180 degrees. They both have in common angle B, so these are going to have to equal the same as that. But in a proof, you have to do all of this measurement. So, we know that these angles are congruent. Means their measures are equal. So I can substitute in and say that two of these measurements of angle BDE is going to equal to two of these measurements of angle A. I'm skipping a lot of steps. I'm substituting in, then combining like terms, and substituting in, and combining like terms. So I'm going to get here. I'm going to divide by 2 on both sides. I'm going to get that the measurement of angle BDE is equal to the measurement of angle A. Two angles have the same measure, then they are congruent. This is probably going to be on your next quiz, this proof. So those of you who are zoning out, I don't know why. Don't know why. So now that we've proven that this angle is congruent to this angle, take those away. Now I can say this item, or this statement in part C, that yes, now I can prove that these two segments are parallel, because in a proof, the justification would be if corresponding angles congruent, so that's what we've got here, these are corresponding angles, then lines are parallel. We are trying to conclude that these segments are parallel. So your justification, your reason, it needs to match your logic. So that's why my hypothesis is corresponding angles are congruent, and my conclusion, what I'm trying to conclude, is lines are parallel, or segments are parallel. So make sure that that is matching your logic and your justification. If you're trying to conclude that lines are parallel, then that better be your conclusion of your justification. Alright, so now we got that those lines are parallel. That means part D says, explain why quadrilateral ADEC is an isosceles trapezoid. You have to prove both of those items one at a time. First off, you need to prove that this is a trapezoid. Whenever you're trying to prove a quadrilateral is a trapezoid, you have to go back to the original definition. The definition states it's a quadrilateral, 4 sides, 4